Hi, welcome back. Today we're going to take a look at higher order partial derivatives. Now, you might recall in calculus last year we did find higher order derivatives. For example, if we look at acceleration, this is the second derivative of our position equation. So let's kind of review. For example, from last year, let's say we were given the function f of x equals 3x cubed minus 4x minus x. And we want to find the first, second, and third derivatives. Well, our first derivative would just be 9x squared minus, that becomes 4 cosine of x minus 1. Our second derivative would become 18x. Be careful, the derivative cosine is negative sign, so we get plus 4 sine x, and that just gets annihilated. And our third derivative would become just 18, and over here, plus 4 cosine of x. So we are taking multiple derivatives, and of course we have different notations. Of course, this is like what we call, I like to call the Newtonian. Leibniz preferred this notation, d2y over dx2, and remember what this is saying is that we are taking the derivative. We are taking the derivative with respect to x twice. Another way we can write that is like this. We're taking the derivative with respect to x twice of our function, of our derivative. Whoops, so this should be dx right there. There we go. We're taking the derivative again of our derivative. There should not be a 2 here. This is just another way to write it. Now this way is going to be kind of similar to what we're going to be doing with multivariable. So, and that's what we're going to be taking a look at today. We can apply the same concept to partial derivatives as well. Although now we have options with which respect to take the derivative and in what order. For example, I could take, if we have a function of x and y, I could take the derivative of x first, followed by y. We can use other notation as well to represent those higher order derivatives. For example, we can take the first derivative in terms of x, and like I said, we can take the second derivative in terms of y. So let's take a look at what this is saying. So this is, I'm taking my partial, remember, it just still says a derivative. I'm taking my second derivative, the 2 there says I'm looking for my second derivative. And this says we're taking the derivative of y, and we got the derivative with respect to x. So the question is, well, which one goes first? Well, it's kind of like over here. I could write this as the derivative with respect to x of my derivative. So what's going to go first is we're going to take the derivative with respect to x first. And we can see that in the notation right here. We're taking the derivative of our derivative with respect to x, then we're going to take it with respect to y. Now for me, this notation is kind of confusing. I prefer actually using our Newtonian. I prefer this notation instead. It's a little easier to read. And what this is saying right here is, if we follow the order of operations, we're going to take the derivative with respect to x first, then with respect to y. Notice in both notations, we take the derivative with respect to x first. Although, here's a secret. Here's a secret for you. Later on, we're going to realize it really doesn't matter the order. Alright, so let's take a look down here. So, as you can see, we're actually going to evaluate this derivative from left to right. So, let's see here. So, we have this function, f of x, that should be f of xy. Old habits die hard. F of xy is equal to x cubed y. We want to take the derivative with the partial derivative with respect to x, then with respect to y. So this is basically saying we are going to take 2 partial derivatives. So the first one we're going to do is we're going to take the derivative with respect to x first. fx is equal to, if I take the derivative with respect to x, y is my constant, we should get 3x squared y. So notice this is with respect to x. Now I'm going to take this derivative with respect to y. Notice when we take the second derivative, we don't go back to the original function, just like up here. When I took the second derivative, I didn't look at my original function, I looked at my first derivative. The only difference is, instead of taking the derivative with respect to x again, now I'm going to take my derivative with respect to y. So f of x, y. Well, y is my variable, the 3x squared is my constant. So if there's a 1 there, I drop my power, I'm left with 3x squared, and the y just disappears. So this is with respect to y. So let's talk about the number of second derivatives. Well, I could take the derivative with respect to x twice. I could take the derivative with respect to x and then y. I could take the derivative with respect to y and then x, and then I could take the derivative with respect to x, with respect to y twice. So notice, if we're taking, how many different how many different second derivatives can we have? There are 4. So we say that there are 4 second partial derivatives. Now later on we're going to talk about uniqueness. Only two of those are the same. So even though there are 4 second partial derivatives, 3 of them are unique. 2 of them are the same. We'll talk about that later on though. So let's see here. So let's say f of xy is equal to 3xy minus 4 sine x plus y squared. We want to take the derivative with respect to x. So let's see here. So if I take the derivative with respect to x, the x just goes away because there's a 1 there. So that's just going to become 3y minus, this is the derivative sine of x, so we get 4 cosine of x. And what happens to the y squared? Well, that's a constant, so that just becomes 0. So there's our derivative with respect to x. If we want to take the derivative with respect to y, now x is my constant, my power rule, there's a 1 there, so I drop it down. I'm left with 3x, the y disappears. The 4 sine of x, that just becomes 0 because this is now a constant for us, and that becomes plus 2y, right there. Let's take the second derivative with respect to x. So we already know that our first derivative with respect to x was 3y minus 4 cosine of x. If I take the derivative again with respect to x, that 3y just goes away, and I'm left with positive 4 sine of x. Remember, the derivative of cosine is negative sine, so it becomes a positive. Next, let's take the derivative of x with respect to y. So let's see here. Remember, my derivative with respect to x was 3y minus 4 cosine of x. And if we take that with respect to y, well, we're left with 3. This 4 cosine of x just becomes 0 because it's a constant for us because we're only looking at the variable y here. Alright, now let's take the derivative of y with respect to x. Well, we know our derivative with respect to y is 3x plus 2y. If I take the derivative of y now with respect to x, when we go to order, y and then x, if I take the derivative of y with respect to x, we're left with 3. Notice, these are the same. I just switched my order, but they're still the same. We're going to talk a little bit more about that. We've already kind of mentioned that a few times here. Alright, so let's take the second derivative of y with respect to y. Well, remember, our first derivative was this 3x plus 2y. And fy, we're going to get 2. Because the x is just a constant right there. Alright, go to video 2 and we'll take a look at a few more examples. I'll see you then.